Well, thank you for coming this talk. Today, I will talk about how we build network switches as servers at Facebook. So hopefully you find this topic interesting. And to illustrate why I'm giving this talk, a little bit about myself. So I work as an engineering manager at Facebook. I support FBOSS team. FBOSS stands for Facebook Open Switching System. And what we do, we build software for our custom switches. And we are part of Facebook infrastructure. But what is interesting and relevant to this talk, I actually never worked in networking before joining Facebook. My past experience were either distributed systems when I worked at Twitter, or for a long time, language compilers and runtimes when I worked at Microsoft. So when I heard about this project, I thought it was so fascinating that I had to be part of it. Things that kind of project was attempting to do was kind of changing the industry. And so I hope by the end of this talk that I convince all of you why is this really exciting. So here is an overview of what I'm planning to cover today. First, I'm going over introduction, just give you context about Facebook network. Then I will talk a bit about how this network was built in the past, and also very important, how we operated this network. And then what were some problems with those ways. And also, probably the biggest and most interesting part of the talk is going to be about the approach we took to solve these problems. And then I'll briefly touch on some new things we are contemplating doing. So let's look at how Facebook network looks like. So first, this is image of all people using Facebook and their relationships. So this is our social network. And as you know, there's lots of people using Facebook and other apps. And in order to support these people and give them good experience, we had to build vast infrastructure. So things like really big data stores, really advanced caching mechanisms, even things like building advanced developer tools to support thousands of engineers working at Facebook. And obviously, that meant building a physical network that can handle this much traffic. So let's look at that network. At Facebook, we usually divide this network in these three big domains: data center network, backbone network, and edge network. Data center network is where all our servers are connected together, usually inside one physical data center building. Then these data centers are in turn connected themselves via backbone network. Backbone network consists of very high throughput optical links that usually go between major metro areas. And as you remember from the previous picture, since this is a global network, some of those links are in undersea cables. For example, we just announced we are putting another undersea cable in between US East Coast and Europe in collaboration with Microsoft, because both of our companies need more throughput and more connection between those two regions. And then finally, edge network consists of POPs, or points of presence. This is where Facebook network connects to the wider internet, as well as where people using Facebook connect to us, usually via their ISPs. So what focus of this talk is going to be, and where we made these changes of how we build network, is going to be in a data center networking. So this is where I'm going to focus for the rest of the talk. So this is how data center network topology looks like. And I know this is fairly complicated. But don't worry, you don't really have to understand why it looks like this way. There are a couple of key components, and I will just kind of make sure as I kind of go through this image to kind of point them out. So on the bottom here are rack switches. So if you know how data centers look like inside, there are lots and lots of racks. They're filled with servers, and on top of that rack, there is a top of the rack switch or RSW. One interesting thing to know just about this part of the network is there is no redundancy on this layer of topology, meaning if the rack switch goes down, all the servers in this rack lose connection. Rack switches connect to what we call fabric switches, which are a bit bigger. An interesting thing is that every rack switch connects to 4 fabric switches. So there's a redundancy on that layer, and the network is designed in such a way that if any one of those 4 fabric switches goes down, traffic is still flowing fine. Then the next level up is where we have these fabric switches connecting to spine switches. And again, they have 4 of them, so there's redundancy on that level. And then the last layer is where spine switches connect to edge switches. Again, there's 4 of them, and that's where the network basically leaves data center. You might ask yourself, why is this so complicated? And the reason is, what we're trying to solve as a problem here is how to connect tens of thousands of servers efficiently together. And efficiently is probably a topic for yet another talk, so just trust me on that. And if we just had a big switch, let's say with 100,000 ports, we could just connect all those servers to that switch and we would be done. But there's no such thing. Nobody invented anything like that yet. So that's why we have to invent these ways and these kind of topologies to connect these servers together. And so far, key points were there are multiple layers, and then there's redundancy on all but the lowest layer in this topology. And the final key point is that in terms of hardware and software, there are different requirements on different levels. So hardware requirements, you can think in terms of number of ports or speeds of those ports are different on every level. And then in terms of software, you can think which protocols these switches need to support, or what's the scale requirements, how many routes they need to be able to handle. So that's the third key point important for the rest of the talk. So let's look how we built this type of network in the past. So we used to build a network by buying network equipment from various vendors. And so these vendors all had a sort of different type of offerings for their customers. So they would bundle software and hardware together, and then they would have the wide array of various offerings, and then customers would pick basically what they needed based on the demands of their networks. What that meant in practice, as we were building and expanding this network, that our network was very heterogeneous. There was lots of different devices from different vendors and from different generations of those devices as we kind of grew over time. So what that meant in practice from operational standpoint was that all of them had different ways to monitor how they're working. They would expose different ways to configure them. So some would have command line interface, some would expose APIs, they would kind of have, or both. So that was very different. And depending on what the vendor offered, you could customize some things or not. What was actually very common for all of the vendors and their devices was that the software updates, apart from some occasional bug fixes, were mostly not happening. So especially if we're talking about major new features, that was not very common. So what would typically happen, device would get installed in a data center, and through their life cycle would kind of go on pretty much unchanged. Again, maybe there's some bug fixes, until they was decommissioned at the end of the life cycle. And then, again, from an operational standpoint, we had teams of engineers who would build scripts and kind of try to deal with all these differences between different devices, trying to automate things and kind of make it easier to operate over time. So I'm sure you can start guessing that there were some problems with this approach, and let me just kind of cover a couple of those. As you can imagine, kind of for a global network like this, it was very, very important for us to automate as many things as possible. And that was pretty hard when you kind of all these devices had different sort of ways to interact with them. Also, to build really good automated tools, what we really needed was looking into internals of these switches and their internal states. And different vendors would kind of give us different levels of visibility, if you want. So it wasn't really, usually we wouldn't get everything we need. The other problem we encounter is even when we did have bug fixes or other major upgrades to do on software and the vendor had them ready, since we didn't do this very often, it took a long time. So any process you can imagine you do, if you don't do it regularly, it just takes a long time. And it is error prone when you have to do it. So the good story I'd like to share about this case is that a few years ago, we decided we wanted to upgrade from IPv4 to IPv6. I wasn't at Facebook at that time, so this is a story I heard. And so what happened was that, so we had to work with all these vendors to make sure that their devices had good IPv6 support. And what we discovered was that as we were testing that we would find bugs. And it was not surprising because most of their customers were still using IPv4, so this was not as mature. But the problem was that as we would report a bug, then we would have to wait a fairly long time to get fixes from these vendors. And then when we would get them, what would happen is that we would find new bugs. and the reason was that they would bundle things together, right? So they would provide fixes to other customers, or they would add features for other customers, and they would bundle everything together and kind of give us a new image. So we had to repeat this cycle several times until we were ready, sort of, and we kind of thought, OK, all of these devices have a good IPv6 support. But then there's another part of the problem. So we started upgrading these devices, and if you remember that topology picture, so upgrading those higher levels, we could manage better because there's redundancy there. But on that lowest level, there is no redundancy on the top of the rack switches. So what that meant when we got a new image from a manufacturer for those devices was that we had to stop traffic on those racks. And we had to do it on every single rack we had in every single data center. And you can imagine service owners who had services running in those racks were not super happy about network team interrupting their traffic. And there's no good automated process to deal with this. So what happened was that we had to start massive cross-infrastructure effort. There were lots of people, lots of teams. Their only job was just coordinating this massive effort to make sure we can kind of go through every single rack and upgrade this. This literally took years. And as you can imagine, it's not something we want to kind of do very often. So that was another problem. The last problem I want to highlight is, as we were building this network, we were trying to stay ahead of the projections of how much of this capacity we need to provide in the future. And this was driving some interesting discussions about, well, maybe it would be easier to support this if we try these new protocols. Or it would be easier to do this operational type of thing and automate more things if we kind of had better visibility into these internals. And without having vendors giving us this support, it was practically impossible. So let's look at our approach and things we decided to do to try kind of do better. And so we decided we are going to design our own hardware and software for network switches. How hard can it be, right? So there's some design principles or kind of ideas people had how to do this better for us. So we decided, okay, we'll kind of separate hardware design, software. We want to make sure that these two things are kind of not bundled as tightly as vendors do them. So we want to have them sort of be able to evolve independently. So if we have a better version of a software, we can just kind of deploy that without kind of worrying about hardware. On the hardware side, we also wanted to make sure that the kind of our hardware is designed in as much as possible in a kind of modular fashion. So because we can't predict future workloads, it's hard to tell what type of hardware for network we're going to need. And so we were thinking if we can design it so it's kind of made up of these modules, then we can maybe combine them in interesting ways. We can kind of be able to go get ahead of these like changing workloads. And finally, with lots of things we do, we decided to open source. So both hardware designs and key software components are open sourced, and they're part of our Open Compute project. So let's look a little bit about what's interesting and how these separate pieces were designed. So here's the way we come to that point of the talk about how this hardware and software is similar to servers and services. So we designed hardware to have, because we already designed servers as a part of OCP project, there are already server designs that are open sourced. So we decided to build on that. And so our switch hardware was designed to resemble very much servers. And what that meant in practice is that it had kind of more memory and more powerful CPUs compared to vendors, because they were kind of more similar to the servers themselves. And the reason why we wanted that is because on the software side, we wanted to be able to run shared components, things we normally use in a Facebook server fleet, to run on servers as well, on the switches as well. And for example, in practice, that means that our software runs on a standard CentOS image that we use on all our servers. But I think the most interesting, actually, and the things that was driving force was that is this key principle of operations over features. Because even though now we are in this business of creating or developing our own hardware and software for switches, we are operator first and foremost. And so what we want is to make sure that what we come up with can be operated easily. Kind of consequence of that is that oftentimes having like a really cool feature that somebody wants to try, but that would make operations harder is like not going to happen. So we sort of want to make sure that even every time we add new thing or try new thing, that we don't kind of change that bar on operations. So let's look a little bit more how this worked in practice. So we started this project, I think around 4 years ago. It took around a year to develop the first switch with a small team of software and hardware engineers. We started deploying these switches in production around 2.5 years ago. We started first from that lowest level in network topology on the top of the rack switch, because those were actually the easiest. The requirements, as their changes, they're kind of easiest on that bottom layer. And today, big parts of our network on top of the rack switches use these switches. We call them wedges. For example, all the new data centers have them. We didn't replace the existing ones. We kind of wait till there's a time to decommissioning and then replace them. And then also, we decided a while back to move to that kind of next layer in network topology in the fabric switches. So we developed those, and we call them backpack. And we started deploying them in production earlier this year. So worked pretty well. This is a time frame of how this happened. So as I mentioned, a couple of years ago, started with the wedge. This is top of the rack switch. It's 40 because it was for 40 gigs networks in data centers. Then we moved down to the fabric switches. And one interesting thing, going back to that principle of modularization, was this is actually designed to be kind of one box, but inside it's 12 wedge switches. We never used this in production much because by that time there was need to start working on 100 gig data centers. So we build 100 gig versions of both of these devices. So that's wedge 100 and backpack. And then also earlier this year, we released wedge 100S that had some more security features. So let's look at some interesting thing about software, which is where I work. So if on this previous timeline and all these different network switches, interesting thing is it all runs the same software. And that was kind of intentional. So what is that software? So there are two key forwarding processes that run on a switch. We call them agent and BGP. Agent is a process that's responsible for programming a special chip that does hardware forwarding. And you might ask, well, and the BGP implements the very common network protocol. So you might ask, why didn't we use this principle we have of designing these switches as servers and just, let's say, wedge 100 has 32 ports. So you can imagine if I just put 32 network cards, and then I have a switch. Why do I need any special other hardware? Well, the reason is wouldn't be fast enough. So if you try to do packet switching in CPU, I think it would be 3 orders of magnitude slower. Maybe with some super advanced optimizations, you could get it to 2 orders, but it's still a non-starter. So the chip we are buying for 100 gig switches, we are buying it from Broadcom, can do 1.6 terabits per second. So we can't really do that with CPUs. So that's what agent does. Agent programs this ASIC, and then ASIC does the hardware forwarding. Other things, there are other things that, and so these key forwarding processes are what makes a switch a switch. But there are other processes that run on these. As I mentioned, we wanted to make sure we can take advantage of things we already had in Facebook's infrastructure. So there are other processes, the things that normally run on all the servers now run on our switches. So good examples of this would be our logging daemons or configuration daemons, or daemons that are in charge of exporting metrics. They just export switch-specific metrics from switches. And then that's all collected by the rest of Facebook infrastructure. One other I guess, manifestation of that principle to design this software, same as we design other things we are already familiar with at Facebook, which is building services, is that both of these forwarding processes are services. And they're more specifically thrift services. So lots of, or most services at Facebook internally use thrift to talk with each other, to do RPC. And then agent and BGP do the same thing. They use thrift to communicate with other services, rest of infrastructure. An agent is open source, so you can kind of go and take a look at that on GitHub. But if you take a step back, you kind of might notice that, well, geez, when I have a service that needs to make RPC calls to some other service in presumably some other rack, I need to have network that's working. And now you're telling me that network is a service as well and also needs thrift and RPC to function. So there is some sort of circular dependency maybe there, or a strange loop, you might say. But it actually works, even though it's a strange thing. We don't need Thrift to bootstrap and start network, so that works fine. You get network first, and then you can make your RPC calls. But this is not the kind of the only thing that's interesting, or maybe these things are the most interesting thing to me. But we are actually now operating network very similarly as how we operate services. So it's very common for large-scale services to be upgraded frequently, and so that's what we do with our agent and BGP. For example, agent gets updated to a new version on the whole fleet every 2 or 4 weeks, 2 to 4 weeks. And when we do that, we again employ the standard practices people do when they upgrade their services in a large fleet. We do canary testing. We find the places in a network that are not critical and deploy the new version. And then we wait and monitor and make sure everything looks good. And then we pick small percentage somewhere else and repeat the process. And then we pick bigger percentage until the whole fleet is upgraded. So that's very unusual. This, as I kind of explained in the past, this was never happening. Other thing you might have noticed is like, well, gee, if you're upgrading this so frequently, how are service owners coping with that? Because now you're kind of touching every top of the rack switch every few weeks. Well, there's this neat feature that the Broadcom, the manufacturer of the chip we are using, has, which lets us save the state of the switch in hardware. And if you're fast enough and reboot into the new version of the key forwarding agent, we can then pick up that state and kind of continue working. So it just needs to be relatively fast, but otherwise there's no traffic interruptions. So that was really cool. And that lets us kind of do these things. And then finally, as with every other large-scale system, failures are common. It's not a question if, it's when. So we had to invest, obviously, in addition to various test systems we have, into disaster recovery systems too. So we have to make sure if anything goes wrong with these forwarding agents and they stop working, that we can recover really quickly, and then we can spend time trying to find the root cause. So what did we learn from this process? So we learned we could move fast, right? There was, several of these hardware iterations, the software, like numerous iterations. It opens up possibilities for us to try, experiment new things. Obviously, now we have visibility into everything, both hardware states, software states. We can build good automation based on that. But we also learned this required certain adjustments, and everybody is sort of working in this part of the infrastructure, which means network engineers, obviously software engineers, production engineers, all of us have to adjust to this new world where these are not just switches and not just servers, but this kind of strange mix of both. For example, network engineers used to go and work with vendors to get fixes or to request features. Now they work with the internal team. There are some differences on how that works and what works, what doesn't. We had to share much more operational responsibilities and learn from each other. But I think that's a good thing. It just kind of gives us all much better perspective on the system. But also, we learned that since now we are upgrading that software fairly often, and we also run other shared daemons or processes that we depend on that are owned by other teams, there are different risks, right? So we had to learn how to manage that because we now have much more complex dependencies. And what's interesting is then on these dependencies we have, the teams that, let's say, provide these shared logging daemons, they do upgrades on their own. So they kind of, when they do changes, and they do the same process we do. they go canary in a subset and then kind of gradually increase that percentage. So we don't control the frequency or when they do that. So they also have to make sure that their changes are now not affecting switches. And when they do, for example, canary testing, interesting things is that they sort of start to need to become aware of the network topology itself. For example, that becomes interesting when, let's say that somebody who owns the logging process wants to test their changes on fabric switches. If you remember, fabric switches, there's 4 of them, and there's redundancy on that level. But if somebody runs something on 4 of them that kind of creates some problem, right, and all 4 of them stop working, then that would be bad. Lots and lots of racks that connect to those would lose their traffic. So they have to start understanding, oh, when I'm canarying my change, I can only pick 1 out of those 4, so I don't kind of interrupt traffic. They didn't have to worry about that before. So let's look a bit about what we are contemplating doing next in this space. So overall, we think this worked really well for us. And so we are constantly learning new things. So our fleet of top-of-the-rack switches is growing as we're building new data centers. And now, as we started deploying fabric switches, same is true for them. But they have different place in the network, so different requirements. So we're still learning from that. But based on that and based on the needs of our network as we expand, is we are going to decide on what other device in our network to support. So which one we want to do next, both hardware and software. We want to be able to use all of that information we have to build even better tools. Lots of stuff that we could do, particularly interesting things around automated remediations. So when things go wrong, if we can automatically fix them, that's really important with the size of this network. Now we finally have some ability to experiment with new protocols and new topologies. So earlier, we open sourced a new protocol called OpenR, and we're kind of very curious to start using and experimenting with this in a data center. It's currently used for other purposes, and we couldn't do this before. So OpenR has some advantages over BGP. Hopefully, we'll try. BGP has been around forever, so we want to kind of try, if we can do something better. And we're hoping a couple of things that might be better are speed of convergence. That's really important in the network's property. Things like simplifying policies. Again, if you remember that huge topology, that's all managed by various policies. So maybe we can simplify that. And also OpenR can help us try experimenting with different topologies. We're also planning not to bring Facebook down because Facebook needs its network. So we're continuing investing in making our disaster recovery and testing systems better and more sophisticated. But there's lots of kind of interesting things that we could still do there. And then we are committed to continue sharing everything we find out and learn in both hardware and software with the wider community via OCP. So we like to say at Facebook that we are just 1% finished. So I hope I kind of illustrated some interesting things, and we are always hiring. So if at the end of this talk I convinced you that this is indeed a very interesting area, there's lots of exciting stuff happening, please let us know. But anyways, thank you.